Good afternoon, students. Last class we have been discussed about the diffraction. Okay, so you can able to observe the what is the diffraction pattern from the figure. You can easily observe that in the case of a best example, which is related to the ocean water waves. So there only if we can observe the diffraction pattern. Example. The thing is that here, uh, what do you mean by diffraction? We already discussed it in previous class. So that maybe gives you that here, whenever a light which is going to be passing through in a media, if any obstacle, if it is going to be placed, the path of the light which is going to be traveling, where the light which can bends at the edges of the obstacle and enter into the geometrical shadow. So this phenomena, we can say that a diffraction pattern. The thing is that here, uh, when you observe the diffraction pattern on the screen, if you are going to be placing such a here at a distance, there only you can observe that at central maxima and at the principal axis, the central maxima, which may have the intensity of the diffracted light, which is more, and toward the central maxima, the intensity of the light, which is gradually decreasing. Okay, so that is the case. Intensity which may be gradually decreasing toward the central max. So that is the case for diffraction. But wherever in the case of interference, uh, there should be a here fringes are going to be formed here. What do you mean by fringes? Means here a bright dark bands. Okay, a combination of bands, you can call it as a fringe here. Uh, so that band is nothing but a fringe here. Okay, bright and dark equidistance. You may observe the intensity is same. Okay, there only the light intensity, interference light. But whereas the for the concept of the interference, there only it is needed here two or more waves. So those have such a frequency or intensity. Those are in coherent, okay, in coherence, and those are in phase. Then only the interference is going to be takes place. Okay, these are the conditions. Okay, now. But here for diffracted light, the light which is incidenting upon obstacle and bending at the edges of the obstacle and which is not stopping at all. But the thing is that here bending and entering into this geometrical shadow. Okay. There only we are placing a screen. On the screen, if you are going to be observing the diffracted light intensity, which is going to be gradually here decreasing toward the central max. Okay. So, but in diffracted light, there only which you may have interference. Getting my point? So, sir, how you can explain me that means here? I will show you the thing is that here, suppose I just want to draw you the diffraction pattern here. So this is the case here. This is the principal maxima. So this is the right side. And whereas, so this is the left side. So here, this is the maximum intensity, I maximum. What do you mean by intensity? The square of the amplitude. A square equals to I. The square of the amplitude is nothing but a intensity. So toward the principal maxima, this is the central one. The intensity, how the intensity which is going to be changing here. You can easily see that here this is the case. Okay. But where is the interference, sir? If you ask me like that. So this is the bright one. This is the bright, dark. This is the dark, bright, dark, bright, dark. This is the right hand side. But what about the left hand side? This is the dark, bright, dark, bright, dark, bright, dark, like that. Okay. So what you are getting here, bright, dark, bright, dark, bright, dark. What you are having? These are the cases. So what are these? These are the fringes. So these fringes you are observing in the case of here where interference. Okay. So that what you are going to understand from this diffraction pattern. Diffraction pattern itself has an interference pattern. Okay. Getting my point? So diffraction itself has an interference pattern. Okay. Sir, how it is means this is the case. Is it clear? So I think so you got. So this is for the diffracted light. We have been discussing about the two types, Fresnel's and Fraunhofer diffraction. And here a source means light, a monochromatic light, a screen, which are at infinite distances from the obstacle. Obstacle means here an aperture. Okay. And here in Fraunhofer, source and the screen are at infinite, whereas in Fresnel's finite distances, and whereas in Fraunhofer diffraction, infinite distances from the obstacle are aperture. And no lenses are used to make the rays parallel or convergent in Fresnel's diffraction. Whereas in Fraunhofer diffraction, we are using the lenses. So this is the most important short question for examination point of view. This question is so many times this question is asked. Okay. So in our laboratory, what type of diffraction we are using means Fraunhofer diffraction. We are going for Fraunhofer diffraction, not by the Fresnel's diffraction. Okay. So that means you are placing an infinite distances from the obstacular apertures, all these sources screen which you are going to be placed. So this is also one of the important concept between the Fresnel's and Fraunhofer diffraction. Okay. And how you are going to find out the intensity of the light. Okay. Resultant light. Based on this only, we are going to finding the R value. R means here resultant amplitude of n simple harmonic vibrations. Okay. So there we are going to be discussing all these things. So this may gives you here after doing the calculations here resultant amplitude value A sine nd by 2 by sine d by 2. Directly we are considering this equation for to find out the intensity of a point at a screen due to the Fraunhofer diffraction due to a single slit or else double slit or else n number of slits. Okay. So this is the case. So there we are using the direct equation, but in examination point of view, they are not going to ask you that how to find out the resultant amplitude of n simple harmonic vibrations, R value, capital R value. Okay. The thing is that you need to know that how the equation is, which is going to be coming out here. You need to know this. Okay, this is the Fraunhofer. We already last class we already discussed it. But what is main important concept? What is the phase difference means 2 pi by lambda into path difference. Formula is important. Okay, phase difference formula is 2 pi by lambda into path difference. 2 pi by lambda into path difference is the phase difference formula. So we are finding the path difference from the figure here. Okay. So we are substituting and we are deriving the equation. So our aim is that you need to calculate the what is the intensity of a diffracted light at a point P on the screen due to single slit, double slit, n number of slits. N number of slits which is corresponds to the grating element. Okay. So all these we have been calculated here. So I value intensity at a point P, that is a square sine square alpha by alpha square. So what are the conditions to get the maximum intensity? If it is a bright one at a point P, what is the condition is to fulfill? If it is a dark one, that means the minimum intensity. What is the condition to fulfill this? Okay. Last class we already discussed. Go through that. And for this is the diffraction pattern here. Okay. So just now we have been already discussed this one. You can easily see that here. I value at central maxima a square sine square alpha by alpha square. Okay. Toward the central maxima, if you are going to be moving right side or left side, how the intensity of the diffracted light is going to be here falling on, you can easily observe this case. Okay. So there only we are observing the interference pattern here. That is a bright, dark, bright, dark. Just now we discussed. Only the thing is that here, the intensity, how it is going to be changing. That is very, very important. Okay. So this is about the diffracted light. And Fraunhofer diffraction, uh, due to a circular aperture, that is also we discussed it here. This is the circular aperture. And due to this, how to calculate the intensity at a point P. Very, very important question. Okay. At a distance x, the point is there. There only if you want to calculate the that means Aries disk, x means radius of the Aries disk. That value becomes 1.22 lambda into f by d. Okay, f is the focal length, and where small d is the here slit width. Okay, so like that, you can easily calculate this value. This may be asked as a short question here. This is the double slit X. Two slits are there, S1 and S2. W W dash is the wavefront here. Okay. The separation, which is small e, and here the intensity which can finding that at a point P due to the double slit. How to calculate this means you can easily observe this case. Okay. So the thing is that here one other extra term which is coming out along with the here for one term in the previous concept single slit, Fraunhofer diffraction due to single slit. So that extra term is a cos square beta. Okay, cos square beta. So this is the interference term, and leftover is diffracted term. Is it clear? Pi by lambda t plus d sine theta is the interference term. So in this pattern only we are having two factors. One is the diffraction pattern, another one is the interference pattern. So that what is the equation here? The resultant intensity at a point P on the screen due to the Fraunhofer double slit experiment means here I equals to 4a square sine square alpha by alpha square. So sine square alpha by alpha square term which is related to the diffraction pattern, due to each individual slit, whereas cos square beta, that that is related to the air interference pattern. Okay, please remember this: double slit or single slit. So the same conditions are to be followed here. If the point P, which is point P means there only we are finding the intensity. Okay, where it is on the screen. So if it is bright one, bright means maximum intensity. What is the condition? And if it is a minimum intensity means dark. So how to calculate? What are the conditions? So you can easily see that. So at central maxima itself, it has, you can see that 4a square sine square alpha by alpha square into cos square beta. This is the one term. Okay. So which may gives you here how to find out the diffraction, how to draw the diffraction pattern. In diffraction pattern itself, what are the terms you can be able to express means here. One is the uh, interference, another one is the diffraction terms. Okay, so those two are the cases. So this is the Fraunhofer diffraction due to grating element. So many experiments are there by using the grating elements. You can easily find out the here. Uh, what do you say? Minimum deviation method. If you want to calculate the lambda value uh, by using the minimum deviation method, by using the grating element, if you want to calculate the wavelength of a light. So what do you mean by grating element? Okay. So in previous concepts, we have been discussed about the either a single slit or a double slit. Uh, there is a slit width is there. Okay, one slit singles or a double slit. But the thing is that here, if you consider more than two slits, there only we are using a diffraction grating element. Here, a grating element is a thin transparent glass material. Okay, a thin transparent glass material. On that glass material, a equidistances of a parallel lines which are drawn on this. Each line which may act like an opaque, that means the light may not be passes through that, but equidistances of lines are there. So from those only the light which is going to be passing through that. So this setup you can call it as a here a grating element. Okay. So by using the grating element, also you can find out the intensity of a diffracted light. But the thing is that here you need to calculate the what is the maximum intensity here, also minimum intensity conditions here, and primary and secondary maxima, primary, like that you can easily find out. So this is the case for a diffraction. Sine square alpha by alpha square is a diffracted, cos square beta which may gives you interference. So you can see that uh, zero order principal maxima toward the central is the zero order. Toward the central maxima, there is a first order n equals to 1, small n equals to 1. Okay. So here that small n which is related to the first order, and if it equals to 1, first order, if n equals to 2 means second order maximum. Okay. But in between them there is a minima. Did you observe that? That is the case. So entirely we are seeing this. But the thing is that if we are going to be elaborated here, the different orders of the principal maxima can be observed. Okay. So this is the case, which is a graph is also very, very important for examination point of. So you can see here. Okay. So this is the central max. Where it is central maxima? This one. This is the central max. Central one. So this is the first order. That means what you are getting? VB GYR means VBGR. Spectrum you are getting. If it is first order, right side toward the central, right side is also first order. After first order, second order. But between them there is a dark, okay, bright, and between them dark, bright, dark, bright. Getting my point? So like that, you have to understand the concept. So this is a very easiest method to understand the concept, which is related to the grading element. Okay. While you are doing or performing an experiment, you can easily observe that how the diffraction is going to be takes place. Okay. So this is the diffraction. You can see that here. Could you able to see here which one is the principal or central maximum? So this is the central maximum. Which one? You can see here. So this is the central maximum. This is the central box. Okay. That means intensity is more. Getting my point? Here, the intensity is gradually decreasing. Okay, bright, dark light. So this may be appeared while you are using the grading element. Okay. So this is the spectrum here. First order spectrum means this one. So toward the central, right hand side, if you move the spectrometer toward the central right hand side, there only you can able to observe the first order spectrum. And also if you move the left side, that is also first order spectrum. After first order, you may have a dark, and later on another spectrum will appear here. So that is the second order. But the thing is that here intensity is decreases. Okay. You can see that here the brightness of the spectrum, which is blurry. Okay. Here we are entering into the dark. Only in this spectrum, only third order, n equals to 1, n equals to 3. Central, first order, second order, third order. Central, first order, second order, third order. Okay. No fourth order. But central also, which may have a spectrum. Why it is not showing? The condition is that here, if you maintain such a intensity, it is also going to be gives the spectrum. But central maxima, which is always having a maximum intensity, a more intensity of light, which is projecting toward the screen. That's why the spectrum is not visible to us. Okay. So this is the case. Next, another important concept is that here Rayleigh's criteria for resolving power. So this is also so many times this question is asked in examination. So what do you mean by this Rayleigh's criterion for resolving power? resolving power of a grating or resolving power of a telescope. Okay. In optics itself, you may have these many of experiments. Go through the lab and you can perform easily the experiment. Without having any theoretical background, you cannot able to perform any experiment at all. Okay. So according to the release, two nearby images. What is that? Two nearby images are said to be resolved. When you say these images are said to be resolved, if the position of the central maxima of one which may coincide with the first minimum of the other one and vice versa, then only you can able to say that these two images, nearby images are resolved. So if you observe the figures or images, so you can easily understand the concept for this. So figure A, which may be giving that here, which is well resolved images. So well resolved images. What is that definition? Two nearby images are said to be resolved when the position of the central maxima, you can see here. So the position of the central maxima of one coincide. This is the central maxima. No? The position of the central maxima, first one, which is coincide with the first minima of the, which one? This one, first minimum. Is it clear? Okay. Or else you can go for this. This is the central maxima of the second one, which may coincide with the first minima of this first one. First minima here. Is it clear? First minima of the this one. You can see. Okay. So this you can say that here these two are resolved. These two are resolved. So what is the wavelength of the first one? Lambda 1. The wavelength of the second one is lambda 2. So in between them, there is a dip. Okay? There is a dip. You can easily observe that. Okay. So figure B is just resolved. You can see that here. Is just resolved. So where it is? Where you can see this is the first maxima, and this is the central, and where it is going to be coinciding. Actually, it has to coincide here. Okay, first minima, but here only it is coincide. Or else you can go for this. This is also. So that these are to we say that just resolve. Figures are very, very important in examination point of. Next, you can see here third figure. These are not resolved. These are unresolved. These two are unresolved. So you can go for that. Here you can easily observe first maxima, which is not coincide with the first minima of other. So that these are unresolved. So here the condition for the Rayleigh's criteria is not going to be fulfilled for this. Okay. So Which one is correct for this definition? Figure A is correct. Okay. So capital A and B are which is showing that which are the central maximum of the diffraction pattern of two spectral lines. The corresponding wavelengths are lambda 1 and lambda 2, and the angle of diffraction of central maxima of the image capital B, which is greater than the angle of diffraction of the first minima of the angle of diffraction of central maxima of the image of capital B, which is greater than that of the angle of diffraction of first minima of capital. So that you have to say that hence both the optical rays will appear well resolved. This is the condition. So you can see which figure B is just resolved. What do you say here? You can say that here the position of central maxima of wavelength lambda 1 and which may coincide with the position of the first minima of wavelength lambda 2, and the resultant intensity curves in the middle. There is a dip, middle dip, which is seen at point C on the image here. So according to this here Rayleigh's criteria, which is going to be saying that these two are just resolved. Next, what do you mean by figure C? Figure C is indicating that here the central maxima corresponds to wavelengths lambda 1 and lambda 2, which are very close to each other. Then these two images which are overlap and they cannot be distinguished as separate images. So the resultant intensity has a peak which is higher than the individual intensities of capital A and B. So the second case set the resolution limits as per the Rayleigh's criteria. Next is the resolving power of grating. What do you mean by resolution? The method of seeing the two close objects. So here two close objects as a separate using some optical instruments, which is called resolution. Okay. So in this case, you can able to find out the what is the resolution power. So the ability of the instrument to produce two separate images, the capacity or the ability of the instrument to produce two separate images of very close objects, which is called resolving. So what do you mean by resolving power of grating? So the ability to show two neighboring lines in a spectrum as a separate, which is known as resolving power of grating, or the other definition is that the resolving power of a diffraction grating may also be defined as the ratio of the wavelengths of any spectral lines to its difference of wavelengths between this line and the neighboring lines such that they can be just as a separate. So all these comes under the case for the resolving power. Okay. So in this case, what is the formula for the resolving power? Lambda by d lambda. So where lambda is the wavelength of the here given source, and d lambda which is the separation or the difference between the uh, two lines. Sir, actually, where do you observe this case means in yellow color of light. Okay. So, which light which may gives you yellow color? Yellow color means sodium vapor lamp. So, white light which may gives you here a mercury vapor lamp, which may gives you white light which may includes the combination of the seven colors. But whereas if you go for the yellow, which is a monochromatic light source, that means only single colored of wavelength, which is related to here a sodium vapor lamp. But the thing is that here the what is the wavelength of the sodium yellow color means here 5893 angstroms. So what is the wavelength here? 5893 angstroms. But the thing is that here 1 Armstrong equals to 10 power minus 8 centimeters. You need to remember this. This is very, very important. 1 Armstrong equals to 10 power minus 8 centimeter. So the thing is that here 5893 Armstrong means here I will show you. Uh, okay. This is for D1, D2. Okay. 5890 Armstrongs, 5896 Armstrongs. So what is the d lambda? Lambda 2 minus lambda. Okay. So lambda 2 minus this is 5896, this is 5890. This is lambda 1, lambda 2. So 5896 minus 5890, which may gives you only 6 Armstrongs. Okay. But what is lambda? This is the d lambda. D lambda is the 6 Armstrongs for the sodium atom lamp, yellow color light. But what is lambda? Lambda is lambda 1 plus lambda 2 by 2. 5896 Armstrongs plus 5890 Armstrongs divided by 2, which may gives you only 5893 Armstrong. Okay. So this is very, very important for examination point of view. Okay. So many problematic questions have been given out. Please do, please do, please do. So here so many problematic questions from this concept. Yellow color means a sodium vapor lamp, which may gives you only yellow color light means here. You don't take it as which is very easy. But yellow color sodium vapor lamp itself, which may have two separate lines. That means one line which is going to be separating. So one is the D1, another one is the D2. D1 is having one wavelength and D2 is having another wavelength. The separation which may gives you d lambda and the average which may gives you only lambda. This is the case. Got it? So you can go for this. So what is the resolving power? So resolving power of a grating means the ability to show two neighboring lines. In yellow color itself, D1 and D2. So an instrument, an optical instrument which is going to be showing the two neighboring lines in a spectrum and which is going to be separate as a two, D1 and D2, which is nothing but a resolving power of a grating. Okay. The same definition which may follows for the telescope also. Resolving power of a telescope. Is it clear? In place of grating element, we are using the telescope by adjusting a adjustable slit. There only if you are going to be closing at some distance, if you are going to be focusing to a mesh which may include the horizontal as well as the vertical lines. So at some distance, if you are going to be closing the slit here by using the adjustable slit, there either a horizontal or a vertical line. That means horizontal lines which may disappear. Okay. And which may shows the only vertical lines in the mesh. Okay. So that is related to the resolving power of a telescope. Here, while you are using a grating element, here two separate lines, images are going to be showing. Getting my point? So here the case method, this is the wavefront, W double dash is the wavefront here. If you are going to be placing a screen, Mn is a screen, central image is P, and XY is a grating element here. And if it is going to be making an angle theta with the direction of the light, and the diffracted light are going to be moving towards the geometrical shadow, there only the screen is placed. On the screen, the diffracted light due to the grating element is to be observed by using the traveling microscope. Okay. So you can able to see that here. Separation. P1 and P2. Is it clear? So all these can be understood by knowing the definition. Without knowing the definition of this, you cannot go for this images. You cannot able to understand the images. Is it clear? So by doing the calculation part, you can go for this here. That is lambda by d lambda equals to n, resolving power of a grid. Lambda by d lambda, you know pretty well what is lambda, average of the two, d lambda, differences of the two images. And n, small n is the order of the spectrum. Once again, I will show you. Order of the spectrum. This is the first order. Second order, second order. This is the central max. Okay. So this may gives you n value, small n value. But what about the capital N? Capital N is the number of lines on the grating element. I already show you here a grating element. Sorry. Equidistances of line. Okay, broadly I'm showing the space. So this is the grating element. Usually you may have 15,000 LPI. What do you mean by LPI means here? Lines per inch. Lines per inch. 1 inch is, what is that value? 2.54. 1 inch equals to 2.54 centimeters. Okay. So here 15,000 lines and somewhat other that is also either 2,000, 3,000 LPIs are also there. Grating units. Okay. So how to calculate? That means here you need to calculate that small capital N, which may gives you number of lines on the grating per centimeter, not per inch. Okay. For 1 inch, you may have 2K, 2000 lines, but for 1 centimeter, how many? 1 inch means here nearly, what is that? 2000 or 15,000 lines by 2.54. This much. 1 into 2K by 1 inch. That means 2000 or 15,000, which may gives you, if you are going to be dividing, you may get per 1 centimeter how many uh, lines which are present on the grating element. That is needed here while you are performing an experiment. You need to have these many of the lines on the grating. Next, resolving power of telescope. This is also 1 minute. So that is the resolving power of a grating element. But the thing is that here another one is also there, resolving power of telescope. So where we are using a telescope means here telescope which is used to see a distant objects which are subtended a small angle at its objective, and which is limited of limit of the resolution, and which may define the angle of subtended as its objective by the two objects, which are seen in just resolved condition by the telescope. Just resolved. These. Okay. Just resolved. Here is just resolved. Not completely resolved. Completely resolved means first image of the central maxima, which may coincide with the first minima of the second. That is completely resolved. Here just resolved. Okay. So resolving power of a telescope. By using this condition is also by fulfilling this here, you can able to find out the uh, what is the equation part for that. Here 1.22 lambda by A equals to x by f. Okay, lambda is the wavelength, the A is the slit width, and where what do you say means here uh, distance between the object, uh, which may be x, and here capital R is apart from the here from the object. Then you can easily find out that here uh, if you want to calculate the at what distance the resolving power is going to be takes place between them, what is the distance is there, you can easily find out. But in our syllabus, we don't have the resolving power of a microscope. So, but I just want to show you the image, resolving power of a microscope is this. Okay. The same definition which may follows here, but the thing is that here, what type of element you are using here, whether it is a grating element or a telescope or a microscope, whatever it may be, then you can easily find out here according to the definition only. This is not in our syllabus. Okay. So this may gives you here diffraction. Okay. So other one is also there. Wait a minute. So this is the resolving power of and dispersion of a grating. Okay, in unit 6 in our syllabus. So this is the Rayleigh criteria. We already discussed it. Can you able to see this? You can see here. This is the central maxima at a distance, the other one. So Rayleigh criteria. Is the Rayleigh criteria is going to be fulfilling or not? We can check it once. So 1.22 lambda by D Rayleigh criteria, theta value. So there is a dip between two images. Okay. Dispersion and resolving. Dispersion of a grating. Dispersion means capital D. So which may measures of the angular separation and produced between two incident monochromatic waves whose wavelengths which are differ by a small wavelength. D theta by D lambda is a dispersion of it. Okay, a small angle, and D lambda we already know that. But the thing is that D sin theta equals to M lambda according to the diffraction. Okay, so there only by substituting you can get. Next is the resolving power of a grating. See here. Characteristics of three gratings. We already discussed this, three cases. In our PowerPoint presentation, this is our textbook. Okay. But in my PPT, I have been showing you how these are to be separating elaborately, how it is going to be gives out. You can easily observe the images of these three conditions. So you can find out the characteristics of these three grading. Okay. So here 5820 Armstrongs is there. So many problematic questions are given out. We can go for this. Okay. At the end of the each chapter, you may have so many problems, particularly from the diffraction and interference. Both these two chapters are the two units. You may have different types of problematic questions. If you thoroughly practice these questions, you can have an idea how to do these type of problems. You can easily and get the marks from these problems. Okay, so that is the case. You do practice for this. By tomorrow, we will discuss about the polarization. So this is the another important concept here. So many short questions you may have. The combination of the short, which may gives you here an essay. Okay. So in this polarization, I just want to give you the outline for the polarization. Plane polarization, polarites. What do you mean by polarites? And polarization by the reflection, reflected light. Okay. So here, what is Malas law? What is the Brevester's law? And what do you mean by refraction, double refraction in a particular crystals here? Okay. What is Huygens principle here? And real and Nichols prism, most important expected essay question is Nichols prism. So all these comes under this polarization chapter. So this we will discuss in uh, tomorrow's class. Okay. So logging off. Right. Thank you. Thank you, Anand.